Hello, yes, my name's Liam. I'm a doctoral research fellow in the medical physics department at UCL. So today I want to talk a bit about the work I'm doing in my fellowship, what I've done so far, why I think it's important and where it came from. So let's start off. What was my sort of vision? 700,000 people in the UK live with autism, a condition which affects how people communicate and interact with the world. And further to that, 1 in 10 people in the UK are neurodiverse, meaning that their brain functions and learns differently. My vision here was to pioneer methodologies using advances in brain imaging technology to enable autism diagnosis to be predicted at the earliest point in life. Now, autism cannot be reliably diagnosed until the onset of behavioral symptoms from around 2 years of age, but differences in brain activity can be observed sooner than this. So what is the actual aim of my work? I want to demonstrate that robust functional networks can be mapped across the whole of the brain surface in awake infants. And I'll talk a bit more about what exactly I mean by that later on. Now, what's the potential impact of this work? It's a leap towards a patient-specific tool to enable reliable autism diagnosis prediction before the onset of behavioral symptoms. And this allows for earlier intervention before future diagnosis, supporting the development of people with autism as best we can, as soon as we can, but also improves our understanding of neurodiversity and other neurodiverse conditions such as ADHD. So how do we image the brain in awake babies? One way we can do this is using FNIRS, or functional near-infrared spectroscopy. Now, this is an imaging method that it uses light to image the brain. What we do is we put a load of sources of near-infrared light and detectors of near-infrared light on the scalp. The sources illuminate the head with near-infrared light that travels through the outer layers of the head, the skull, the scalp, and into the brain. Now, near-infrared light is more preferentially absorbed by blood compared to the surrounding tissue. Now, when a region of the brain is activated, more blood flows to that part of the brain to cope with the increase in oxygen and energy demand. But what we tend to see is an overcompensation in blood flow. So we tend to get an increase in blood concentration in a region of the brain that's activated. So we see an increase in oxyhemoglobin concentration and a decrease in deoxyhemoglobin concentration. What this basically means is that a region of the brain that's activated absorbs more light when it's activated compared to when it's at rest. And so these changes in hemoglobin concentration, that we can see them as a marker of functional activation. And we can use functional near-infrared spectroscopy to study that response. Now, more specifically, the technique that I work with is diffuse optical tomography. FNIRS, but with a few differences in how we analyze the data. So the key difference in diffuse optical tomography is we want to get an image. We want to localize where the concentration changes and activation is happening. Now, to do this, we need a head model. We need some way to simulate how light travels through the head to get our forward model. And we can then use that forward model, combine that with our FNIRS data, and reconstruct an image localizing these concentration changes to the cortex itself. So the definition I'm just going to give to diffuse optical tomography is it's a technique that uses FNIRS data and a structural prior to reconstruct an image localizing hemoglobin concentration changes to the cortex. So that's a brief outline on the imaging techniques that I'll be talking about. Now, here's a couple of statements. The brain, babies have relatively thin scalp and skull, and that enables high levels of near-infrared light to illuminate the brain. And FNIRS and diffuse optical tomography, as such, are often applied to studying development of the brain in the first few months of life. So I'd like to introduce the group I'm a part of at this point, the Diffuse Optical Tomography in the Human Brain Research Group, or DOT Hub as we call ourselves. DOT Hub, it's an interdisciplinary research group focused on advancing diffuse optical tomography for the human brain. And a lot of the work from our group over the past few years has focused on developing imaging devices to replace bulky optical fibers, like we can see in the image here, and replace those with wearable electronics. An issue with the bulky fibers is it limits the use of FNIRs to study babies interacting with their environment, certainly if they're constrained by their movement is constrained by these fibers. But also by getting rid of these bulky fibers, we can more densely pack sources and detectors onto the head. An example of what we've been working on is this sort of design, a modular design that we've come up with working with the spin-out company Gower Labs. And in each of these hexagons, you can see on this cap, they can each contain 3 sources of near-infrared light and 4 detectors. What this means is we can more densely pack source and detectors onto the scalp, and this increases our image quality, our signal to noise ratio, and our image resolution. Now, we've applied this work successfully. I've highlighted a figure from a publication of one of my colleagues, Elisabetta Fria, who published this study she led last year using this new highly dense way of sampling the scalp to image the brain. We've come up with these groundbreaking images, really precisely localizing where activation is happening in the brain. And to build on this work, what's important is to increase how much of the brain we're actually covering. We can see on the image on the previous slide, we are covering quite a lot of the brain, but what if we could cover more? And that's basically the basis of what I'm thinking of the work in my fellowship. How can we expand coverage of the brain? What's the most that we can expand the coverage to? So a brief tangent, I'd like to just introduce the concept at this moment of functional connectivity. Now, we've been talking so far about regions of the brain being activated, but functional connectivity is a slightly different context, a slightly different concept. Now, functional connectivity refers to the statistical relationship between specific physiological signals in time. Now, what does that actually mean? Functional connectivity in diffuse optical tomography in this context looks at what's the correlation between hemoglobin concentration changes in different parts of the brain. And so while I'll be talking about brain connectivity, and this is basically what I'm talking about, how correlated activation is between different regions of the brain. So I'd like to, at this point, revisit the my aim for my fellowship, which is to demonstrate that robust functional networks can be mapped across the whole of the brain surface in awake infants. Now, why do we want to do this? Well, principally, what we see in autism is differences in how functional connectivity and how brain regions link up with each other. And I'm going to highlight a few of these studies. A study that came out earlier this year found differences, a robust pattern of connectivity alterations in children and adults with autism. A study from 2019 found that there are differences in functional connectivity between infants at different levels of risk of autism, differences between infants at high and low family risk of autism. And a study from 2018 pointed out that in infants as young as 4 to 6 months, the degree of activation we see to particular stimuli can predict whether these infants can predict the symptomhood of autism that we see in infants in toddlerhood. So what am I actually trying to do? I'm aiming to develop diffuse optical tomography to study functional connectivity across the entire cortex in awake infants. Now, there's sort of 3 distinct challenges I see here. There's to study functional connectivity, I need to focus on methodology development, developing and applying functional connectivity methods to use with diffuse optical tomography data in particular. There's also a hardware aspect to this to try and maximize how much of the brain we can actually cover with sources and detectors of near-infrared light. And lastly, what I want to focus on is a proof of concept study, applying this to infants to show that we can get robust functional maps, looking at how different brain regions link up with each other. So I'd like to just quickly look at the hardware development. Now, as I've said several times, the focus here is to sample as much of the brain surface as we possibly can. In order to design the hardware to do this, I was looking at different ways that we could that we could use landmarks on the head to try and systematically place our modules across the head. And while that's all fantastic, there's nothing that quite replaces getting your hands on pieces of Velcro and just trying it out on mock baby heads. So what we've got here is the sort of the first stage of the design process. So this is a mock 6-month-old baby head with a Velcro mat on top, and then we got the docks for the source detector modules, put Velcro on the other side, and just started putting these in different arrangements on this fake head to see how much of the brain we could feasibly cover, how much of the scalp we could cover. Now, what's important to recognize here is that hexagons don't tessellate on a sphere. So one of the real considerations for my work here is thinking which brain regions do I really want to focus on, and which regions can we sort of deprioritize. What I really wanted to focus on was the side of the brain, the temporal lobe, and certainly we can see in the lateral view that's where we're seeing the highest density of these source detector modules. So this was all fantastic. I'm working. Having finalized the design, working with the spin-out company Gower Labs based at UCL, we took it to the next stage to see, right, how is this actually going to look if we've taken this through the manufacturing process, and are there any changes we need to make? Luckily, this process went quite smoothly, and here we are with the next stage, looking at how we could fit the light guides for this particular arrangement. Taking it forward now to looking at how we punch the holes into the cap to let the source and detector shine light into the head. And here we have the final cap all put together, which to me seems a world away from when we were playing with Velcro. But this is the cap that I've been working on, the cap that I'm working with, to maximize the coverage across the cortex to see as much of the brain surface as we possibly can. So that is a nod to the hardware development. Now, looking at the software development, let's go back to thinking about functional connectivity. Basically, what's the correlation between hemoglobin concentration changes in different parts of the brain? Now, what I want to focus on is developing and applying functional methodologies for DOT data specifically. So thinking about differences in noise, thinking about how do we implement this specifically with DOT data, which presents challenges that we can't translate straight from established techniques we see with other imaging methodologies such as positron emission tomography or fMRI. So I just want to highlight an example, a study that I've been involved with my group, looking at mapping different networks of brain regions in the adult brain. This is a fantastic image from a paper recently submitted by my colleagues Julie Uchitel and Borja Blanco, mapping the different sorts of regions in the adult brain. Now, I'm really excited to apply these methods and further develop these with infant DOT data. Now, another point I want to make about the methodology development is this specific step here, the head modeling aspect. Now, ideally, for diffuse optical tomography, a head model would be created from each individual's MRI scan. That would ensure that the highest accuracy and that we could get the best model possible of how light travels through the head of that particular participant. The problem, particularly for infants, is this really isn't practical. To MRI scan each individual really undermines the benefits of DOT, its portability, its low cost, for instance. So one thing that I'm looking at and I'm working with colleagues abroad on is looking at how how to design head models based on pre-existing MRI data that we can use in place of subject-specific MRI data, and how best to implement those head models to ensure the highest level of accuracy in diffuse optical tomography forward modeling. This is something that I have looked at in past, working with neonatal infants, working with data from the Developing Human Connectome project based at King's College London. And I'd look to use the skills and expertise learned here and apply that to looking at older infants at around about 6 months. Which brings me on to the proof of concept study I'd like to look at. What I've seen from the literature is that at around 4 to 6 months is the earliest we can see differences in neural signals from infants who go on to receive an autism diagnosis. This seems to be the earliest possible point in life so far to predict the onset of autism or autism symptoms in toddlerhood. So that's why I'm focusing on 6 months infants, and I'm working in collaboration with the fantastic Birkbeck Baby Lab. Now, what I want to look at is social and non-social interaction. So this is relevant in autism, as it's a condition that affects how people communicate and interact with the world. So I want to see in a cohort of typically developing infants, can we see differences in how the brain connects during social interaction compared to stimuli such as toys that don't represent a social interaction. And I'd also like to look at resting states, so where the infants are as still as they can possibly be, and not involved in any particular task, and to see whether we can resolve the brain networks that we see during fMRI with infants, which can only be done while they're sleeping. So, what are my future plans? Well, the principal thing I'd like to do is to demonstrate whole cortex functional connectivity analysis using measures from across the entirety of the cortical surfaces, and this hasn't been done before with awake infants outside of an MRI scanner. Having conducted a proof of concept to show that this technology works and we can resolve differences in connectivity between different brain regions and between different social contexts, I'm aiming to start a new infant study to resolve differences in connectivity between infants at low and high risk of autism. And finally, I'd like to develop methods to conduct effective connectivity analysis. Functional connectivity tells us whether there's a relationship between the activation in 2 different brain regions. What effective connectivity looks at is a causal direction, which brain region affects another brain region. And I'm really excited to bring that to diffuse optical tomography as it's been implemented but limitedly with FNIRS. That's a quick introduction to my work. I'd like to thank these fantastic people based at University College London, the Centre for Brain and Cognitive Development at the University of Birkbeck, and also colleagues from the BabyPal Lab at Cambridge University. And I'd also like to thank the spin-out company Gower Labs for supporting this work. I'd also like to acknowledge my fantastic group, Diffuse Optical Tomography in the Human Brain Research Group, and I've been funded as part of the UCL EPSRC Doctoral Research Fellowship Programme. Thank you very much for your time, and I look forward to any questions you might have.
Thank you so much, Liam. Yes, if anyone does have any questions, please do put them in the chat or the Q&A. Alternatively, you can put your hand up and I can unmute you as well if you wanted to ask the question out loud. So Liam, we've just got a couple of questions in the Q&A. It's instead of using fiber, what do you use to emit the light into infants' heads? And I think it's a sort of part 2 from the same attendee. Infants have thinner skulls, yet I have no idea why they need high light power.
Thank you for the questions. So on the first point, a lot of the work is looked into miniaturizing the electronics. So what we see with the wires and the connections, it's still there, but very much miniaturized. So the basic setup here is because the light that's emitted from the source is the electronics miniaturized into those hexagonal modules, and the data is then there are then wires to take the detected light intensity data. So there's a wire that's coming away from the cap, but that's the only wires that we have, and that really reduces the burden of having bulky wires. And to your second question, I think to clarify the point I made, so infants don't need a higher light power. What we see with adults is that the detectors need a higher gain, yeah, I made a statement earlier on about infants having relatively thin skull and scalp. What that means is that we can image, we can more easily image the brain and get deeper into the brain than we would be able to look in adults. So hope I've addressed your questions there.
Thanks so much, Liam. Just a question from me. Do you receive better data when the infants and babies are in the resting state or when they're active?
I think ideally, to answer your question, ideally you'd have less motion in with infants. So theoretically, you'd have better data with the resting state task. Now, a real issue with that, though, is that infants become fussy and ironically start to move more during the resting state task than compared to a task where it's something a lot more entertaining. They're being presented with something a lot more entertaining. And I think a big challenge that I'm facing at the moment is coming up with a resting state task where infants don't become fussy, but we still get meaningful data.
Fantastic. We've just got another question here in the Q&A box. Apart from unveiling the onset of Alzheimer's, which other diseases or issues can be exposed by studying the brain of a 6-month-old infant?
I think this is a really good question because a lot of our work with infants has looked at infants in an MRI scanner, not interacting with the environment around. So I can't address that question directly other than saying that autism and other forms of neurodiversity can be studied here. But one reason I wanted to go into this project and to do this project was to enable us to have a way to look at what's going on in babies while they're awake, while they're moving about. So I'm hoping that this technology can be applied to looking at different forms of different conditions beyond neurodiversity.
Fantastic. We have another comment and question. Thank you for a great talk. You mentioned that you identify parts of the brain to focus on in your study. I think temporal lobe was mentioned. What other parts of the brain are you focusing on regarding your study on autism?
Yeah, so it's a real focus in sort of social, studying the social brain looks at the superior temporal sulcus and temporoparietal junction. Another part of the brain's been looked at a lot is the inferior frontal gyrus. Now, a lot of in past FNIR studies have had their arrays, have their source and detectors lined up to sample those specific regions of the brain. Because we know that they have the biggest role, but what we don't know is what other brain regions involved. For instance, the parietal lobe. So those are sort of regions that I want to focus to focus on, and yeah, so they're the main regions that I want to look at and make sure that we had coverage on. But also to sort of extend coverage as much as we can to other brain regions to see, are there other brain regions involved in these interactions that we just haven't been able to see because our coverage of the brain has been too limited.